So the first relevant question to our presentation is, why artificial reefs? In many coastal communities, the reef is an important part of the natural ecosystem and the economy. Reefs can be used for ecotourism, which is the visiting of a place to see its ecology, and they also attract fish, which is helpful to fishers. However, in recent years, we've seen a marked decline in the presence of natural reefs due to pollution and raises in open temperatures and the effects of sedimentation. So some coastal communities have turned to building artificial reefs. These are constructs, things that these communities build and submerge into the ocean in order to fill the position of what a natural reef would do, namely attracting fish. As natural reefs become rarer and rarer, artificial reefs will become more and more important. And so it's important to know what exactly defines a good artificial reef.
Before analyzing our data, we felt the need to perform a comprehensive literature review so as to formulate our analysis. Hawaiian reefs are fringing reefs, thus they develop close to shore. These reefs are made of 4 zones. Both the reef flat and reef crest are too shallow and the seaward slope too deep to allow corals to grow. Only the buttress zone, which experiences intense sunlight and abundant oxygen, allows coral to grow. Artificial reefs can be found off of the Waikiki shoreline in the buttress zone. These are man-made structures which help to promote marine life in desolate areas. In 1988, Jean-Marie Thierry described and created an outline of 2 different types of artificial reefs: bottom reefs and floating reefs. He states that these reefs can change current patterns as well as trap plankton so as to prevent animal dispersion. These reefs also directly affect fishermen by increasing fish numbers and protecting animals from predators.
Brock and Norris conducted a study of 4 different types of artificial reefs as compared to a naturally occurring one. These 4 reefs were concrete pipes auto bodies, tire modules, barges, and concrete cubes. The efficiency of the reefs were measured in how well they enhanced the local fish population. They found that all reef designs enhanced the fish population. However, the most effective was the concrete cube reef. They concluded that the careful deployment and assembly of the concrete cube reef led to its greater success as compared to the tire modules, which were just dumped off the side of a barge. The concept of void space has been discussed as a major factor of the success of some artificial reefs. A study was conducted by Sherman and others to compare a common artificial reef unit called reef balls with 2 different modifications: streamers, designed to attract fish, and concrete blocks designed to reduce void space and increase reef complexity. The study found that streamers were ineffectual while the reefs with blocks attracted the most fish. They thus concluded that streamers do not add much benefit to reefs while blocks do, although they note that their study cannot be extrapolated to other sorts of circumstances. The studies that Bradley and I mentioned are only a few of the papers and articles that we looked at in the course of writing our literature review.
Artificial reefs have ranged from waste products dropped off the side of a barge to carefully designed and deployed reefs. In the Florida Tire Reef of 1972, tires broke loose from the cords holding them together and spread over a large area of ocean floor. They prevented new life from growing as well as damaged already existing corals and cost approximately $3.4 million to clean up. Japan has been noted for their long usage of artificial reefs. Around 1850, Japanese fishermen discovered the use of stones to promote the growth of Japanese kombu. Since then, concrete and iron structures have been created and then placed onto the ocean floor known as tsukiso. These attract abalone, shellfish, lobsters, and other sea creatures and have helped to create a seaweed cultivating industry worth over 30 billion yen. Although our research differed from some of the information that we included in this literature review, we kept these examples in mind as we started to collect data and analyze the results.
We will now discuss the methodology of our project. With the help of Atlantis submarines, we were able to collect data on the reefs that were placed on the ocean floor. Atlantis Submarines is a company that owns the world's largest passenger submarines. Thanks to them, we are able to do our project. Here is a map of some of the locations that Atlantis submarines will visit during their normal dive cycle. The first reef that we would encounter on any Atlantis dive is the natural reef. The natural reef is the area between artificial reefs. It tends to have fewer fish than any artificial reef. The next reef, and the first artificial reef that we would encounter, are the UH pyramids. They are a series of flat surfaces stacked up in a pyramid. They were constructed by the University of Hawaii and have lots of flat surfaces for protection. Next are the Asahi reefs. The Asahi reefs are a series of cylindrical steel coils constructed in the shape of a triangular prism. They were made by the Asahi Chemical Company of Japan and have no flat faces, so current passes through them easily.
Next is the Mitsubishi YS-11 artificial reef. This reef consists of 2 airplanes which were sunken in the early 1990s. In 1992, Hurricane Iniki hit Hawaii and severely damaged this artificial reef. Now all that remains of the 2 airplanes are their wings and short sections of the fuselage. The YO-257 is a large metal vessel formerly owned by the United States Navy. Atlantis Submarines purchased it, sanitized it, and sunk it. It was actually the first artificial reef that they placed. Due to its size, the top of the boat is very close to the surface of the water, allowing for much sunlight and thus coral growth. The final artificial reef that would be seen on Atlantis Submarines dive is the San Pedro. This wooden vessel was sunken after an incident involving a fire and a large quantity of teriyaki sauce. Today, the boat's main wooden bridge has collapsed and provides an excellent resting point for small fish. On each Atlantis Submarines dive that we undertook, there were 4 of them. We had 45 minutes of time in total to observe the reefs. In order to make the most of our time, we used the visual census method, which is basically you count the fish that we see. And to facilitate this, we executed constant video recording of what was going on outside the submarines. As we progressed further into the project, we developed more advanced ways of collecting data, including running multiple tapes on the same side of the sub, and developing a vertical oscillation method so that we could see more volume of water at any given time. However, there were some notable problems with this data collection method. While the visual census method is the method that is agreed upon by most of the studies in our literature review as being the only humane and relatively accurate way to count all the fish, it does have some noticeable problems. First of all, from inside of a submarine, it is sometimes difficult to see past certain obstructions, such as the boats. These provide a lot of sheltered area inside, and fish do rest in these places. So any estimate based on the visual census method will almost always be an underestimate. Furthermore, the conditions of the water during a specific time of day are not necessarily indicative of the conditions during the rest of the day. So you have to accept when you are going down that your data only applies for the amount of time that you were down there, and it cannot be extrapolated to any other time of day, which was why we executed multiple dives at different times of days. Furthermore, we had some problems with the resolution of our video cameras, which made it difficult to identify certain species. Another problem was that the absorption of red light made it difficult to distinguish various colors of the fish, and so identification had to be executed based on shape alone. In order to interpret our data, we created a spreadsheet with Microsoft Excel, entered every single fish we believed we had seen into it, so that's a total of 62 species in 25 families, and we watched the videos in full, counted every single fish that we saw, and inserted it into our data sheets. This is a sample of some of our data. This data is 1/16 of the total amount of data that we collected for our project.
After we tallied our data in the data sheets, we made graphs to help us analyze our data. The first type of graph that we created is a bar graph. On the bar graph, we put the locations of various reefs on the x-axis and the amount of fish spotted on the y-axis. In order to make our graphs more readable, we built these graphs on a logarithmic scale with a base unit of 10. We also created pie chart graphs that show a composition of various fish at any given reef. Here are examples of our 2 graphs, the top being the bar graph and the bottom being the pie chart.